what I'll talk about today, it's something I'm excited about, some new matrix concentration inequalities, but I'll sort of present them quite a bit as a tool, right? So as maybe some of you have used in the past, when you have a random matrix whose spectral norm you need to understand, maybe you're trying to study a spectral algorithm to say cluster a graph or to find some structure in a graph or do community detection or something like this. And you need to understand what the spectrum of your perturbations or your noise looks like in order to understand how good your algorithm is. And oftentimes this amounts to computing some spectral norm of some matrix, or you're trying to understand some semi-definite programming. And you want to understand, you try to build some kind of dual witness and you want to argue that your dual witness is a proper one. You need to often understand the spectrum of random matrix. And so random matrix theory has a long history, or at least a relatively long history, but it focuses a lot, or it has to tend to focus a lot in models that are sort of very symmetric, very structured, symmetric models of random matrices, such as Wigner matrices and things of the type I'm sure many of you have seen, or Wishart matrices, matrix of Gaussian entries, or covariance matrices of Gaussian samples, like if you want to study a random sample covariance. But in many applications, right, when we're dealing with graphs, networks, with forms of signal processing where it makes sense to talk about matrix, maybe you're doing low-rank matrix completion, things of this style, oftentimes the matrices don't have all these symmetries, right? They're sort of structured to the problem we have in hand, and we still need to understand its spectrum. Right? And there's these incredibly useful tools that go by the name of matrix concentration, of which I'm going to give a prototype example. Right? There's this really nice, you should take a look, definitely, monograph by Joel Traub, maybe from 2000, beginning of the 2010s, I think. It's where he has many of these inequalities, most of which are extremely useful. I've used them countless times in my own research to when I needed to understand the spectrum of some random matrix. And one that I want to show you today, just as an example, is matrix Bernstein. Okay, so let's see matrix Bernstein, what it says. What I'm going to talk about today is how to improve this inequality. Okay, so matrix Bernstein inequality, you should read about it. I mean, Joel Traub has an amazing monograph on this. I think it's called Matrix Concentration Inequalities. I highly recommend reading it. So what it says is if I have Z1 through Zn, right? Let's say that they're independent self-adjoint matrices. Okay, so independent, right? And symmetric, okay? Just because everything I'm going to say can be in reals or complex doesn't really matter. Just call them self-adjoint matrices, such that expected value of Zk is equal to 0. Spectral norm of Zk is bounded by R for all Zk, say almost surely. Okay. Think, like with numbers, you have things like Chernov's inequality, Ofting's inequality, Bernstein's inequality, right? Now we're doing the same thing for matrices. So it says the following: for all t bigger or equal than 0, we have that the probability that the spectral norm of the sum, okay, so I'll write and then we'll try to process it. The sum of Zk being bigger or equal than t. This is smaller or equal than twice times d, where d is the dimensions. I should say d by d matrices. Maybe I should add these. Okay, times exponential. Right, if you have just scalar, if you just have scalar Bernstein in mind, it will look extremely familiar. Okay, 2 sigma square plus 2/3 RT. Okay, the only thing I have to tell you is what sigma is. So sigma square is basically the spectral norm of the expected value of the square of the matrix. Okay, sounds like a lot of words, so let me write it. That's this is sum k is 1 n of expected value of zk square. Right, the same thing as just taking the expected value of this matrix square. Because if I were to square the sum of the zk's, right, the only terms that would survive would be the terms where, right, if I were to expand the terms in which a zk shows up with another zk, so it's the same thing. Okay, so I don't think I can overstate how useful this inequality is if you ever have to control the spectrum of matrices, right? You can, so I don't know, maybe 8-9 years ago, Joel came to, I was in Princeton at the time as a grad student, and Joel came and gave a talk where he talked about this inequality and some other inequalities that he'd come up with. And I had been working on some synchronization problems that came from signal processing and some community detection problems in graphs. And as soon as I saw this talk, like an hour after the talk, I had already solved my problem, just because like it was dead easy to apply this inequality, right? I didn't know it. I saw this talk and it was completely immediate that this gave me exactly what I need. Within an hour, I had solved my problem that I've been thinking about for quite a while. Now, in some of these examples, this inequality, or in some of the examples I was interested at the time, and I mean, many others that I'm interested in now, this inequality suffers from a problem. And the problem is this dimensional factor D. So let me see if I can come. So this dimensional factor here, right? Sometimes it actually causes, it's normally, if you look at just Bernstein with numbers, you don't have this dimensional factor, but they're matrix of dimension 1, so it wouldn't show up anyway. But this dependency on this tail on D causes lots of suboptimality in many results. And so the goal of the talk today is to show you a version of matrix Bernstein in which this dimensional factor is gone. So I should say goal of today. And I'll present the inequality so you can try to use it in your own problem. Right. So it's a version of, I'll try to, I mean, said like this, it sounds kind of like strange, right? I have there's one parameter, I just want to take it away. It's not clear at all why this parameter matters. Why wouldn't you be able to take it away? So I'll try to give you some intuition of why it matters and why one should hope to actually be able to do this, right? Without this dimensional factor. This is something that we've been trying to do, on and off for maybe 7 or 8 years now. And the moral of the story, and as you'll see, I'll try to convince you of this, is that somehow this dimensional factor belongs here if the matrices are very commutative, and it doesn't belong if the matrices are very non-commutative, whatever I mean with that at the moment. Right? Things being commutative is clear what I mean. Things being very non-commutative is not clear what I mean, but I'll try to make this a bit more clear. So take that moral for now, and let me try to convince you of this phenomenon. So let's focus. You have here a very general inequality, works for any z's, matrices z's, as long as they're bounded, independent, and centered. But really the core problem, I mean, you'll sort of have to wait. Okay, somehow something. Sorry. Okay, it's back here. Okay, good. So the core, the core problem is really to understand. Just the expected value of the spectral norm of a matrix for X being Gaussian. A Gaussian matrix, right? X is D by D. Self-adjoint, right? Same thing. Okay, I mean, I'll try to convince you of this in a second, but I'm saying that, this seems like a complicated thing, very general thing, but actually the core problem lies already in just trying to understand the typical value, the expected value of the spectral norm of a matrix, and we can even focus just on Gaussian matrices to start with. Okay, and why to go from I mean, okay, this is sort of hand wavy, but once you have the Gaussian result, to go from Gaussian to sort of more general, to go from our general random variables, there are tools for this. I mean, the name for these kinds of things usually is symmetrization. Right? Once you have a Gaussian inequality, oftentimes you can transform it into a more general inequality. To go from things like expected value of the spectral norm, right, to things like tail bounds, which is what we have over there. Right, you can usually use concentration inequalities like Talagran concentration or something like this, for example. Right, the point is, by the time you're going from, you're already talking about the spectral norm, so it's already just a number. So then you can use scalar knowledge to go from expected value to the tails, and you can do this quite strongly. And to go from self-adjoint things to general matrices, there's a trick, which, I mean, I'm not going to go, there's no need to explain it. Maybe some of you know it, so I'll put the name, which is called Hermitian dilation. It's really very simple, is if you have a matrix that is not symmetric, you build a block matrix where you put 0 blocks in the diagonal and you put X in one of the corners and X transpose in the other. This now is, or X star if you're over the complex numbers, is now a self-adjoint, and the spectrum of this basically encodes the spectrum of X and vice versa. So really what we want to understand is, once we understand the expected value of the spectral norm of X, we sort of understand everything. There's some work that goes into actually transforming into a general tail bound, but it's something we can do. And for a Gaussian, it's useful to write the X Gaussian, right, as a sum of independent matrices, right? The same way that if I have any Gaussian vector, right, I can write it as a sum of, I can take the spectral decomposition of the covariance matrix, and I can just write it as a standard Gaussian times a vector plus standard Gaussian times another vector, and so on, right? Because any Gaussian can be obtained by a matrix times a standard Gaussian. I can definitely do this with matrices too, right? So I can reformulate my X being Gaussian by taking matrices A1 through AN, right? This will be deterministic D by D, self-adjoint matrices, like the deterministic. Okay. And now I can just take X to be, say, sum of JK AK for K equals 1 to N, where the G Ks are just standard Gaussians, all independent, of course. Okay, just to connect this a bit, right? So clearly any matrix of this written as a series like this is a Gaussian matrix, right? It's a sum of each one of them is just one Gaussian times a matrix. The sum, of course, is Gaussian there because it's independently Gaussian. And any Gaussian matrix can be written this way. Just take the spectral decomposition of the covariance matrix of the entries of the matrix, right? So it's like some n square, d square by d square object, but everything still applies. Okay, so we'll think of our matrices this way. Okay, so let's see what we know then about the expected value. Let me see. Okay, this I wasn't expecting. Somehow it's not creating another page. Strange, give me a second, because this is not the setup I usually use because I'm traveling and I tested everything except creating a second page.
Maybe this continuous mode.
Do you see? Yeah, but I didn't see continuous. Otherwise, I'll just create another document.
Can you go back to
the options that you
to the options? Yeah.
Yeah.
And there's continuous mode. Maybe now.
No, it's still not. It's okay. I'll just create a new document. It kind of makes me feel a bit silly, but okay.
And here you can set the pages in the new document. It said like.
Okay. All right. So let's do this properly then. It's a little strange that. Okay, but I don't have a keyboard here. Okay, so let's just I'll set up a document each time. Sorry for the technical hiccup. The jewels of Zoom talks. Okay, so So one or the inequality to control the spectral norm, the typical spectral norm of Gaussian matrices is so-called non-commutative Khinchin inequality. So let me tell you this, one of my favorite inequalities. Okay, so this is due to this Picard. Here. Okay, it says the following. Again, same setup, A1 all the way through AN. In KD by D self-adjoint matrices. Again, take X to be the series. It says the expected value of the spectral norm of X is smaller or equal than square root log D times sigma, where sigma is given, basically by the same thing as before. It's sigma square is equal to the spectral norm of the expected value of X square. Another way to write this is the spectral norm of the sum of the AK square. Right, this is just the same thing. Okay, so, let me just very intuitively explain to you that you would expect, you really expect that it will be at least sigma, right? Because, right, okay, let's ignore the fact, let's not, let's instead look at the problem of expected value. Or let me do this in another color. Let's look at expected value of, spectral norm of X squared. It's not quite the same thing as looking at the expected value of X, but, because this is a scalar random variable that will concentrate very strongly. Usually when you have a scalar random variable that depends on many, many random variables, right? So the scalar random variable depends on all the G's, right? There's lots of concentration inequalities to tell you that this concentrates very well. So this should be similar to the square of the expected value of X, right? I'm being hand wavy here. Okay, this is definitely bigger or equal than, right, by just Jensen inequality, right? If I move the expectation inside of the spectral norm, I get smaller. And then this is equal to sigma squared. So we expect, the spectral norm of X in the best case scenario should look, the expected value of the spectral norm of X should look like sigma. This is sort of the right parameter. But non-commutative Khinchin gives us a square root log D. Okay. And the question is, when is it that this square root log D belongs here? Okay. Now, because it maybe takes okay, maybe I should still show you that this square root log D is exactly the D from matrix Bernstein. If I have a way of going back to the other thing, you can see it. Because, right, if you look at the typical value of what happens here, right, you have to pick a T such that this is small. And this D will go inside as a log D. And so we will fight against the T square, like the T will have to be bigger by a factor of root log D. Okay, again, hand wavy, but worth seeing. So, okay. See. Okay. So the real question, the key question that I'm interested in is when is root log D factor needed? So, maybe it's never needed. Right? I argue it is needed sometimes. Okay. So let me give you a very simple example on where it's needed. Take a diagonal matrix. Okay, so take X, so diagonal matrices. Okay, so take X to be a matrix where you get a G1 here, G2, and so on, and a GD, and zeros in the off diagonals. Okay, you can of course build this by just taking AK to be EK, where this is the canonical basis vector, EK transpose, just a matrix that's 1 at entry KK. Okay, so what's the expected value, right? Let's compute sigma square. This is what? This is the spectral norm of expected value of x squared. So what is this? X squared is just the matrix with the diagonal elements being the GI squared. The expected value of the GI squared, they're just standard Gaussians, are just ones. So this is just spectral norm of identity. This is just one. Okay, but what is the expected value of the spectral norm of x? Again, we can be a bit intuitive. What will this be? This will be the expected value of the largest diagonal entry, right? This is the matrix. Understanding its eigenvalues is very simple, right? So it'll be the max over k of gk. Okay. And we know that indeed this looks like, right? This will be of the order of root log d. Right. If you don't know, if you don't know that it's of the order of root log d, at least you can very easily believe that it should grow with d, right? Because if I have more and more Gaussians, I'm taking the maximum, there should be a growth, right? And the growth is exactly root log d. So here it definitely belongs. Okay. And the key observation is that these matrices, they commute, right? These, I can view this in two different ways. If I take two random samples of x, they commute, or all these matrices, they commute. Matrices commute. Okay, let me give you another very, very simple example, which is of Wigner matrices. So, this is sort of the simplest, but the little silly example of random matrices because there's nothing spectral or matrix about it. Right? It's just numbers and max of numbers. So let's go into the first sort of real random matrix. These are Wigner matrices. Okay, and the model here is the following: X as independent, or I should say, IID N01 entries everywhere. Just constrained to be symmetric. It needs to be self-adjoint. So like you draw the top half, and then you fill in the rest. Okay. Clearly, I can do this with, I can also do this. I just build my A's indexed by IJ, and I can build them as EI, EJ plus EJ, EI, right? And I can build this matrix this way. Okay, if I'm with the complex, I need to be a bit more careful, but let's not worry about that for now. Okay. And now let's look at this. So what's the expected value of x squared? Okay, here we have to do a little bit more math, but not really much, right? I take x squared. I'm basically taking inner products, right? Because it's self-adjoint. I'm basically taking inner products between, let's focus just on real. Let's say everything is real. Then I'm just taking inner products of rows of x, right? But it's not so hard to see that you'll get 0 in expectation if they're different rows, because everything that gets multiplied to each other is independent. And you'll only get when you're taking the inner product of the same entry. And in there, you're going to get the expected value of the L2 norm square of the row. So the sum of the expected value square of all the entries. And these are basically, you get n entries. So this is basically n times identity, or d, sorry, because the dimension was d times identity, right? So spectral norm of d times identity. So this is d. Okay. And now you can ask, okay, this would something I can't do here on the fly, but the expected value of the spectral norm of x looks like, this goes back to the work of Wigner in the 50s, I believe. And it is of size 2 square root d. Okay, maybe you've seen these pictures. The spectrum of it actually looks like this semicircular law between -2 root d and 2 root d and so on. Maybe you've seen these very nice pictures of semicircular laws. Okay, the point is that there is no log here, right? This is a constant times sigma. It is not square root log d times sigma, right? It is in particular, much, much smaller than what non-commutative Kinshasa would give you. Then square root log d times sigma. Okay, moral of the story is that these matrices very much do not commute. Right? Clearly, all these matrices, they don't commute. And if I draw two Wigner matrices, they're complete, their eigenspaces are completely randomly distributed. And so they really don't commute. Okay, and so the key idea is to sort of, guiding principle is that Wigner matrices don't commute, right? Or say two independent Wigner matrices don't commute. And I was particularly interested in using these inequalities when I was talking about my random matrices tend to be like adjacencies of graphs or Laplacians of graphs or things like this. And I'm very much in this Wigner type world, right? Because sometimes the edges are random, independent, or things of this type, and there's a lot of non-commutativity for sure. Okay, and so the idea is how can we improve over a non-commutative Kinchin, exploiting the non-commutativity of the matrices. And so before I do that, I'm actually going to prove non-commutative Kinchin for you. Okay? Even though it looks like a sophisticated inequality, and it is a sophisticated inequality, I'm going to prove it in like 5-10 minutes. Okay, so we're going to prove, I'll skip some details, but I'll mostly prove it. Okay. So now I'm going to create another document. Sorry. So, okay. Then, okay. Then, okay, so let's see a proof. Right, of non-commutative Kinchin. Yes, the idea is to use the moment method, so-called moment method, it's common in random matrix theory. And the idea goes as follows: you take the expected value of trace of x to the 2p. So take p integer, integer. Think of it large, Okay, so what's the idea, right? I'm taking the trace of the matrix X, just sums all the eigenvalues. Because I'm taking the matrix to some positive power, it's now summing all the eigenvalues to the power 2p. So they're all positive. So at least there's going to be no cancellations. And if I take it to a high enough power, then I'm basically only looking at the largest one, right? This is the key idea behind the moment method. Okay, so let's do some calculations. Okay, so what is this? I have to expand X as the sum of GK, and I get something now. What the formulas are exactly doesn't matter, but there's some features in it that I want you to see. Right, to get all possible ways of choosing, indices for all I'm summing over 2p things. And I get GI1 product, GI2p, right? And then trace of GI1, I2p. Okay, I haven't done really anything. I just expanded. Okay, first observation, these terms go to the only terms that don't disappear are the terms in which a Gaussian shows up an even number of times, right? Only non-zero, right? Only non-zero if each term, each GK shows up an even number of times. Right? If it shows up only once, then the expectation will be 0. Again, so I have to now look at the sums over all places where indices show up an even number of times. Okay, so there's some kind of it seems at least annoying combinatorics to do, but there's a very nice formula for it. So I'll just give you the formula. Okay, so this is known as Wick's formula. And basically, you can sum over only so-called pair partitions. Okay, so I partition the two to the p indices. So I sum overall. So sum over all possible partitions of 2p. So pair partitions, what it means is I have my numbers, let's say, like 1, 2, 3, and so on, all the way to the 2p. And I take a pair partition of them means I split it into pairs. Maybe I don't need this. Actually, a very nice way of representing these is saying 1 gets paired with 2, 3 gets paired with 6, and 4 gets paired with 5, and so on and so forth, right? And so this is one way of representing partitions. Okay, so you should have this. This is like an example of a mu. Okay, so I sum over all possible partitions, and then I sum over all possible ways of indexing the matrices that are with respect to that partition. Yeah, I mean, this is a bit notation heavy, but there really isn't much to it. Right, so all possible ways of picking, the indices such that it's compatible with the partition, and then I just get traces of, and basically the expectation goes away. Okay, now comes another idea. Won't be able to prove this, but we'll have to trust me here. So idea, commutative case is the worst one. Right, and what do I mean by this? Is that if I take this quantity, okay, then in absolute value, this is smaller or equal than what I would get if I were to do the partition where everything shows up together, right? So, okay, so let me write this partition here. If 1 gets paired up with 2, 3 gets paired up with 4, 5 with 6, and so on. Okay, so if things were commutative, then any partition looks the same, right? Because I can just reorder the A's. And then this partition that I drew here in blue is very easy to do because, right, I always get A I1 square, and then I always get A I2 square, and I always get and so on. So really, this is just the sum from K from 1 to N, right, of AK squared to the P, right? Because if you expand this sum, what do you get? You get all possible choices of I1 through IP. You get AI1 squared, which means AI1, and then AI2 squared, right? Because there's a square, which means you're doing the 2. You get first the first squared, then the second, and so on. And so if they were commutative, then this partition in red would correspond to this one. And so this idea that commutative case is the worst says that any partition, the value from any partition absolute value is smaller or equal than the trace of this, which is what you get when you do if you were able to commute and sort of put all the indices that match together. Okay, I mean, this needs to be proved, but it may sound at least believable. Okay. So, and this, I mean, in this form, like without any constants, like, with the right constants, so on, is due to code from, I think, like 20 years ago. Okay, but what does this mean? This means that the expected value trace of x to the 2p, right, is smaller or equal, okay, it's positive, right, and they're just going to use triangular inequality all over the place, right, smaller or equal than the number of pair partitions times this term. Okay, so let's just do that. The number of pair partitions times the trace of square to the p. Okay, the trace is outside to the p. Okay. Now let's try to, just do very simple combinatorics. How many pair partitions there are? It's basically smaller or equal than 2p double factorial, right? Because you pick the first one. This one needs to be paired with somebody, right? There's like 2p minus 1 possibilities. Then that one gets paired, right? You start by picking who gets paired with the first one. There's 2p minus 1 possibilities, and then you need to write that. Then one is picked. Then you take the next one that's free. There's now 2p minus 3 possibilities, and every time you decrease by 2 the number of possibilities, and so it's actually 2p minus 1. I just write 2p. Double factorial, it's like a factorial, but instead of multiplying all the numbers, you just multiply every 2. And here what we get, right? So the sum of AK squared was in spectral norm bounded by sigma square. So this matrix, sum of AK squared to the P, is bounded in spectral norm by sigma to the 2P. And then I have the trace, I can get at most dimension times that. So this is smaller or equal than dimension because of the trace times sigma to the 2P. Okay. Okay, so we're almost there. So now, by just Jensen, the expected value of the spectral norm is for sure smaller or equal than the expected value, right, of trace of x to the 2P to the 1 over 2P. Right, in the spectral norm, I'm just taking the largest one. Here I'm summing all of them, even to a high power, and then only taking, taking the power to the 1 over 2P outside the expectation. Okay, and so what do I get here? I get 2P double factorial, 1 over 2P times d to the 1 over 2P times sigma. Okay, so now let's stare at this for a second. I haven't picked P yet, so I can pick P whatever I want. And I want to pick P in order to make the d to the 1 over 2P disappear. Right, I want that to be a constant. So basically this forces me to pick P to look like log d, right? Because if I take P to be log d, then this basically becomes a constant. Okay, because I don't want a big factor of d. But what happens to this term? Right, what does 2P factorial look like? Right, 2P factorial, I mean, let's not worry too much about the constants, but 2P factorial is basically I take 2P and then I multiply by 2P minus 2, then 2P minus 4, and so on. I'm basically multiplying something that looks like P, right, or 2P, P times, right, because I'm doing every 2 integers and I start from 2P, so this looks a bit like, say, 2P to the P. Okay, I mean, it takes a second to see, but it should be at least believable. And so this means that if I were to do this, what I get, right? So let's see. So then what do I get? Let me go to the other pen. Get smaller or equal then. Right, I get 2P to the 1 over 2P. So I get 2P, say, square root times there's some constant. I mean, this is all up to constants, right? D to the 1 over log D is just a constant. I won't care about this times sigma. But since I take P to be like log D, I'm effectively getting the square root log D times sigma. What went wrong in the, I mean, and we pick up exactly, you just saw the proof from non-commutative. Now, what happened? Where did these terms come from? They came from the fact that there are too many partitions, right? I have P to the P partition, right? And these are just too many. And the key idea is that, so key idea, most partitions have crossings, or key idea to improve, right? I mean, I just proved non-commutative kinship, but to improve, most partitions have crossings and should have more cancellations. Okay, so let me try to convince you a little bit more of this, and then I'll show you our inequality. I mean, in a way, terms, if you have a term like trace of, say, some AI, right? You have a matrix AI, then you have a bunch of stuff in the middle. I think of it like some random stuff. And then you have some AJ, and then you have some bunch of stuff in the middle. Then you have an AI, and then a bunch of stuff, and then you have an AJ, say, and then a bunch of stuff again. If you have something like this, right, then clearly each term is showing up an even number of times. So, right, so it will be counted. But in the language of the partitions, you will have something like this, right? And then like there'll be many more things and so on. But it's not so hard to see that you might expect cancellations, right? Because the AI maybe has an eigenvector that's very large in the direction. Now it has a bunch of stuff in the middle. It rotates this eigenvector around, right? And then it hits a j, maybe puts it somewhere else. And then by the time it reaches, right, you take the products and reaches the AI again, this large eigenvector might be pointing in a completely orthogonal direction. And now when it hits AI, they don't, right, they don't create the double of the eigenvalue. It's a different kind of cancellation than just summing plus or minus ones, but it certainly feels like a type of cancellation that one should be able to exploit. Okay. And so the core idea is to exploit this. Okay. And so the sort of the first time this was done in this setting dates back to Joel Traub. Okay, so now I'm mostly, I mean, I showed you the results of a classical, proof of a more classical result, but now I can sort of explain how we do what we do. But so let me first tell you the first instance of this from like 5 years ago is due to Joel Traub. And what he did was he came up with a parameter that sort of tries to measure how much these terms should be smaller. And this parameter is what he calls the matrix alignment parameter. So, you know, W of the random matrix X will be the following. Okay, to the power 4. Okay, it's like a new sigma, say. You take the maximum over all unitaries. I mean, don't worry too much about the unitaries, but so unitaries. And then you take spectral norm and you take the sum over all ij from 1 to n of ai, the unitary, ai, sorry, q1, aj, q2, ai, q3, aj. Okay. Spectral norm. Right, the q's are sort of representing the rotations that might happen in between. Okay, and with this parameter, what he was able to show is actually that the expected value of the spectral norm of X is smaller or equal up to constants, then log d to the 1/4 times sigma plus log d square root times this parameter. Okay, so it's very much in this direction that non-commutativity should help. And so what we do is but okay, one issue is that usually these inequalities are used in certain regimes where these parameters are like auxiliary parameters are a lot smaller than sigma, and sigma is sort of the typical, the value that you actually want to capture, that you believe your random matrix behaves like sigma. And so it's particularly important to get, at least in some regimes, to get actually sigma. And not a logarithm, like there's still a dimensional factor, just a dimensional factor is enough. And so what we do in this talk, we remove, I should say, I'll show you an inequality that we remove this log there. So goal is to remove this log d to the 1/4 and to have nothing. Okay. And so I want to leave some time for questions, so I won't show you the proof of how one does this. But I can still show you sort of very quickly the idea. And the idea is you could imagine, okay, so an idea. How do we do this? And then I'll show you the actual inequality. Let's go back. Let's take back this, let me write back this moment method, trace of x to 2p. And now it's the sum over the partitions, just like I did before. But now I'm going to separate between the partitions where the arrows cross and the partitions where the arrows don't cross. And now I have sum over mu of what's called non-crossing partitions of size 2p, right? And I have the same thing, sum over f in v of trace, you know, af1 and so on, af2p, okay, plus the terms that have a crossing. Okay, what I mean by a crossing, right? If I have things like this is no crossings. If I have things like this, then this is a crossing. Okay, let's say for a second that we had a way of actually making these guys not matter, right? We had a way of arguing that these are small, or maybe even 0. Then we could do the exact same argument, but instead of having to count how many partitions there are, we would only have to count how many non-crossing partitions there are. And now it's known from combinatorics, and this, I mean, this is how, if you've seen proofs of the semicircular law and so on, this stuff shows up, that these are very related to the so-called Catalan numbers. And these are actually smaller or equal than 4 to the p, not p to the p, crucially. And so this means that when we do our, if you are able to do this, I haven't said that we're actually able to sort of forget those terms, but if you are able to forget those terms, then you would get a 4 to the p. And so when you take to the 1 over p, you get a 4 rather than a square root p, and the logarithm disappears. And so with this kind of idea, I mean, the actual, I can say 2 words about the proof. If the AKs are non-negative, you can make this kind of argument work. For general AKs, the way we actually do this is we build another random matrix, okay, using ideas from free probability, something in operator algebra. We build another random matrix for which this is true, that every time something crosses is just 0, right? It's actually some kind of infinite dimensional object that in some limit, whenever there's a crossing in these formulas, is 0. And so there we would have everything we want. And then we interpolate between our random matrix and this one, this object. And we just show that as you go from one to the other, things really don't change. So because the terms were very small there, they're also very small in our world. Right? This is typical in probability. People do this often, these interpolation techniques. Okay, and that's the proof. That's as much time as I have to describe the proof. But I think this intuition of where the commutativity is helping or hurting is sort of more useful than the proof itself. So let me show you our theorem. Okay, so our theorem. Okay, we show that expected value spectral norm of x is smaller or equal than 2 sigma, the sigma parameter, as before, plus a constant times, and now there's a different parameter, one that's actually much easier to estimate, and I'll tell you what it is, log d to the 3/2. Okay, so here I don't think we get the right power of the logarithm. This we don't know how to do, but let me tell you what v is. So vx is the covariance of the entries of x, the spectral norm of the covariance of the entries of x, or maybe like vx squared. Okay, so you take the matrix x, right? Your random matrix x, Gaussian matrix, you compute its covariance. By this, I mean, of course, it's a d squared by d squared matrix, or, a d squared over 2, because, these things are all symmetric. And now you compute the spectral of that covariance. So this is something that's usually very easy to do in problems. Okay, and the point is that this parameter is related to that alignment parameter, but in general, an example is much easier to compute. Actually, essentially no example where one can compute the matrix alignment parameter that is not by bounding it by this one, or very, very few examples. Okay? And there's a few features that this has. So actually, this is much, much more general than just a spectral norm. Essentially, what this does, because it's comparing with this sort of limit object where crossings don't matter, it just says that all the spectrum looks like the spectrum of this limiting object, right? Which if there's anyone who knows free probability in the room, we can call this like x free, the free version of x, in the sense that, if you don't know what free probability is, you can just imagine the sense that every time I do one of these expansions, crossing terms are 0. So we show that the spectrum is completely just converges essentially once this parameter, this covariance is small, converges to the one of x free. It's better in general than 2 times sigma x, because sometimes the spectral norm of x free is smaller than sigma x, so you get sort of exactly the right answer. And you can also show stronger symptotic freeness. I mean, it's only if someone works in these fields, they know what this means. And if you don't, that doesn't really matter at this point. Okay, so let me give you I could show you a few examples where this gives some, significant improvements. But I want to instead show you the actual inequality. Like once you have this Gaussian inequality, you can transform it into a Bernstein type inequality. Okay, so I'll show you that. And then examples, you can imagine things like let's say I have independent entries, but with very different variances, where most entries actually maybe have variance 0, and there's some in very even potentially worst case placed entries, you have some variance, right? It works well in those cases. Or you have, say, a Wigner matrix, and you decide to glue entries to be the same. So like a pattern matrix, maybe you have a random ankle matrix or random circulant matrix, or something where there's still some independence in the entries, but some pairs of entries are forced to be the same, right? It will be very easy to compute the covariance, to compute sigma, and so on. And there's many examples of this style, and I think we're looking for more. So let me give you the actual inequality, and then I want to leave plenty of time for questions. Okay, so what we call a matrix concentration inequality. Okay, without the D. So theorem Z1 through Zn, independent D by D matrices, where expected value of Zi is 0, and they take X to be at the sum of the Zi's. Okay, now I have to define a laundry list of parameters. So okay, so let me do that. So mu square is equal to the covariance of the entries. These are all things that are relatively easy to compute. There's sort of something measuring non-Gaussianity, which is the expected value of the max of the overall I of the Hilbert-Schmidt norm of each of the Zi's. But these are things that are generally quite easy to compute. I mean, not always. Okay, there's a sigma star parameter that this one looks complicated and it's not easy to compute, but it's always smaller than, okay, so let me write it. Okay, this one looks complicated and in general is not easy to compute, but you can just upper bound it by the sigma if you like, and the inequality is still true. It's just sometimes you can do better by using the stronger parameter. But Bernstein doesn't use the stronger parameter, we just use sigma. Okay. And now the variance parameters. So I mean, here I didn't make the matrix symmetric, so I have two variance parameters, but if they're symmetric, they're the same. It's just the expected value of X star X, right? And second one, right, is exactly the same as before, just I'm writing in full generality. Okay, and this is equal to, I mean, certainly smaller than the max between the sigmas. Okay, then we have that the probability that X is bigger or equal than 2 times sigma 1 plus sigma 2 plus universal constant times log D to the 3/2 mu plus log square. The point is that, all these nu and L and sigma star and so on, they're always, or at least definitely nu and L, they are much, much smaller than sigma, right? So these kinds of dimensional factors on these terms are not so important. The important thing is that there's no dimensional factor on this term. Star root T plus RT is smaller or equal than exponential of minus T. Okay, and this essentially recovers, I mean, in a certain sense recovers Bernstein. And when nu and L, or especially when nu is much smaller than sigma, then it will give you Bernstein without the dimensional factor, right? There is no dimensional factor here, there's no log there. Okay, so I want to make sure that I give time for questions, so I'll stop here. You can, in the paper, you can see a few lists of examples, but think of structured Gaussian matrices. It could be that you take a very complicated graph, and now you take the adjacency matrix, and now you replace everyone in the adjacency matrix by a Gaussian and a random variable, for example, even though there might be a lot of geometric structure in the graph, which will give a lot of geometric structure where the zeros are in this random matrix. This will still work, and then you can still use all these inequalities, even though they don't have the symmetries that random matrix normally has. Okay, thank you so much for the attention, and I'm happy to answer any questions.